Hi, welcome to Unit 52. In this unit, we're going to talk about the power of the source of the energy of the sun. I know I mentioned in the previous unit, I think it was Unit 51, where we talked about the fact that the sun produces a lot of energy, and we said that now we know where that energy is coming from. How do we really know that? Okay, so here is basically what we're going to discover in this unit. We're going to discover the fusion inside the core of the star, nuclear fusion, that is. We're going to talk about the proton-proton chain. That's not the only way to produce energy, by the way, inside the core of the star. We explain the role of neutrinos in fusion, and that's key to the question I just asked, basically. How do we know what we know? If we can find the byproducts of these nuclear reactions coming from the sun, then we know that this is true. Okay? Not just we find them with the right numbers. Then we know what we know. Because here is the thing. We have a model. This is what we think is going on inside the sun. Now let's go and test that model. Let's go and do an experiment and see if that model corresponds to the reality. And it does. That's how the answer to this question. Okay. So describe a role of each of the four forces. You will see nature comes in four forces. Force of gravity, which is the weakest of them all, by a factor of 10 to the power 40. I mean, it sounds too, it sounds small, but it's really not that. It's super small. It's a quantity that you cannot even imagine how small it is compared to the strongest force, which is the nuclear force. There are four nuclear forces. There is the weak nuclear force and strong nuclear force. Both of them, including gravity, is present. And, not to be outdone, the electromagnetic force is also there. The electromagnetic force is actually essential too to the process. The strongest force in nature is a strong nuclear force, followed by the electromagnetic force, followed by the weak nuclear force, and then in a scale that you cannot even imagine comes gravity. But all of them are present when it comes to the core of the sun and how the sun produces its energy. Again, the basic idea came from when Mr. Einstein came up with the expression that connects the energy to the mass of an object. Okay? If you take a nuclear reaction, chemical reaction, they do that, but it's an amount that is negligible. We talk about other sources of energy in a chemical process, like the burning of fuel inside the car, for example. Excuse me. But when it comes to nuclear reactions, that phenomenon is far more exaggerated. If I measure the mass before of the products that went in and measure the mass of the product that came out, so these are reactants, these are products. If I find the difference between them, the difference between them goes into energy according to the expression that E equals to mc squared. C is a constant. C is just 3 times 10 to the power 8 meter per second, or 300 million meters per second. You square it is going to be 9 times 10 to the power 16 meters squared per second squared. So it's just a number. It's a fixed number. So it's the exchange rate, if you wish. If you have 1 gram of mass, you can convert it to this much joules. And the conversion ratio is just the speed of light squared. That's all. That's what the expression is saying. Of course, it was a major discovery. Immediately after that, scientists like Gamov and also Zwicky and other people, they came up with this model. And now that's basically the working model for how the sun produces its energy by fusing lighter elements. And each nuclear reaction has a potential of producing energy, and we'll see how the process works. Okay. The first element in the whole thing is gravity. Gravity is the one that brings everything closer and closer together. Without gravity, the sun would not exist. We would not be there. So it's gravity is the one that starts to pull things together because it's an attractive force. If gravity was the only force, everything would fuse up to a point at the black hole. Everything in the entire universe. The force of electromagnetic force, gravity, by the way, acts at infinite speed. So it's going to pull anything infinite speed, infinite distances, I'm sorry. So it's going to pull anything and everything from whatever it is, from all stretches of the universe toward one another. Electromagnetic force, though, also has an infinite range, but it has two kinds of forces. If you bring two similar charges, actually they repel one another. Up to a certain point, that's fine. I mean, it's probably not going to mind, but if they get close, no. You can't get any closer than that. So it's without it, again, we would not exist. The sun would not exist, because if that repulsion does not exist, everything will collapse on one another. So we're good to have actually electromagnetic force. The electromagnetic force in this case balances things, because what is fusing are the protons inside the core of the sun. But protons have no charges on them, no electrons with them. They have positive charges. They don't want to be close from one another. They repel each other. You need tremendous temperatures, and that's the role of gravity, to bring everything close enough to reach that 15 million Kelvin inside the core of the sun. The temperature is high enough that the protons can get closer from one another. They cannot get that close either, because even with that temperature, electromagnetic force will repel them. But there is something in quantum mechanics called quantum tunneling. At some point, the proton finds itself next to the other proton, even though there is a barrier due to the electromagnetic force. And if it crosses to the other side, the weak force comes into play now. So you see how? So far, three forces came into play. The weak force changes one of those protons into a neutron. And now all of a sudden I have a proton and neutron, that the fourth force come into play in this case in here. It's going to fuse them. So we start with gravity pulling things together, temperature increases, electromagnetic force keeps things apart so that it doesn't, you don't want it to be too crazy either. Because if the electromagnetic force was not there to regulate things, the sun would have run out of energy immediately if it was formed, and then we would not be here to discuss it. So you need the electromagnetic force to prevent that rate from getting too high. So again, now you're close, away. As a matter of fact, the probability of one of those protons converting into a neutron is so low. But it's high enough on a global scale because we have a lot of them to produce a lot of energy from the sun. So now one of them converts to the weak force, and when it does, it fuses due to the fourth force, which is the strongest one, and now it keeps them together. So what formed in this case are heavy hydrogen. This hydrogen has a proton still, and that's what makes it a hydrogen. Hydrogen have in their cores protons, positive charge, but also it has a neutron, so it's a heavy one. It's actually twice the mass of a single hydrogen. In addition to that, that proton that converted into a neutron has to release that positive charge, which is going to be a positron, which is an electron with a positive charge. That's not the only byproduct, though. This neutrino that does not have a charge is necessary to balance the electron that just came out, or the positive electron. So a positive electron comes out, which is an anti-electron, so you need a real neutrino to come out of the byproduct. So that's really why we have that. So again, you have two protons, two similar products come out, which are neutron-proton. One of them is positive charge, the other one has no charge. So there must be a positive charge going somewhere, and that's carried by the anti-electron. Electrons in general are negative, but this anti-electron is actually positive. It has the same charge as the one that the proton used to carry. But since you produce an anti-electron, you need to balance the electron property by having a neutrino, which is actually of a flavor electron. Okay? So that's basically what the process is. So in here, we're talking about the terminology used in this case. We have a neutron. It's similar in mass to a proton, slightly more massive, but that's negligible compared to everything else. And then you have the proton. Those are what exists inside every nucleus of every atom. Hydrogen itself is made up of a single proton. Heavy hydrogen, or deuterium, it has actually, there is a third version of this hydrogen, by the way, that has actually two neutrons and one proton. That's even heavier than this, okay? But the deuterium is the first isotope. We call them isotopes when they have the same protons, but they have more mass. In this case, they have more neutrons. So in this case, this is a different isotope of hydrogen. And the same thing in here, I have 2 protons. Remember, helium has 2 protons. But this one is a light helium, helium-3, because it has only 3 what we call nucleons. These are called nucleons. So it has 3 nucleons, namely 2 protons and a neutron. That's not a stable, by the way, atom, stable nucleus. But this one is more stable. This is the one that we find in nature, helium-4. Again, that's an isotope. Both of them are isotopes of helium. This is the standard helium. This is the lighter version of this helium, okay? Okay, this is the process. This is the proton-proton chain. It's like if you take a mirror and you put it in here, everything that is happening on the left side is happening on the right side. So we're going to focus on the left side. What we're saying is happening on the left side is actually happening also on the right side. So on the left side, 2 protons moving super fast due to the high temperature inside the core of the sun. They get too close from one another. They fuse and produce the heavy hydrogen, deuterium. The byproducts are a positron, which is a positive electron, and a neutrino. Neutrino is going to be unimpeded. They don't interact with anybody. For the most part, they go straight through. As a matter of fact, if you put your hand like this, there are billions of neutrinos that went through it every second. So there are a lot of them. But they don't interact because they don't have a charge. They're super light. They don't do anything. They go straight through everything, for the most part, okay? Which presents a challenge in trying to detect them. So we're going to talk about that. And then we have a positron. Positron is a positive electron. That's not stable because the minute it encounters an electron, remember we have a lot of electrons because we have an ionized gas inside the core of the sun. So it takes a fraction of a second before it meets one electron, a random electron in there, and that they will annihilate one another. They will cancel one another. And they will produce 2 gamma rays. Why not just one? Gamma rays are supposed to be photons, light. Why do we are requiring 2 of them? It has to do with the conservation of momentum, not just the conservation of energy. So you add this mass, and that's the energy of this gamma ray plus this gamma ray. But you need 2 of them to conserve the momentum because the 2 proton, the electron and the anti-electron or positron, they come from different angles. So your outcome also must conserve the momentum, not just a magnitude, but also as a vector. So you have 2 of them. Those are the first energy that is produced by this whole process. So it starts in here somewhere. And then now I have a floating, again, heavy hydrogen. It meets a regular proton, regular hydrogen again, and they collide. And one of the electron fuses to both of them through the 4th force, of the strongest force, the nuclear force. And now we have a light helium because we have 2 protons and 1 neutron and another gamma ray. Okay, this gamma ray and these 2 gamma rays are almost the same energy. So, albeit this one, this is 28 mega electron volts. Probably these ones are higher, okay? But it doesn't matter. It's a lot of energy in either case. You can't see them anyway. That's the main form of energy. Remember, all of this process up to this point is similar and identical to what's happening in here. So when I said 3 protons came in here, 3 more protons came from the other side. That's the source of the whole thing. 6 protons, 6 hydrogen atoms produced a lighter helium in this case and a lighter helium, and the 2 lighter heliums will meet and they produce 2 protons and a regular helium. So how many protons came in? 1, 2, 3, 4, 5, 6. That's the hydrogen. How many the final products are? 1, 2 protons. So out of the 6 that came in, 2 came out. So in the net, if I do a balance, only 4 came in because the 6, the 2, the other 2 that came in went out. But I also have helium. In addition to that, I have gamma ray, gamma ray, gamma ray, gamma ray, gamma ray, and another gamma ray. This takes about 100,000 years just for them to escape the core of the sun before they hit us. a question was raised in another unit is, if the rate of this nuclear reaction increases, obviously we'll have more gamma rays produced. But we will not find out until 100,000 years from now that the sun is actually more active. Or if the activity goes down, also we will know until 100,000 years if we're tracking just the gamma rays. But there is another two products that came off of that, and they're these neutrinos. They go unimpeded. It takes about 8 minutes or so for them, slightly more than 8 minutes for them to arrive Earth. So if there is more increased activity inside the core of the sun, how do we find out? Through the neutrinos, more of them will be arriving. If there is a decrease in nuclear activity, there will be a decrease in the rate at which neutrinos are being detected. That is really what is at stake in here. That is how we know what's... So the neutrinos are actually going to tell us about the state of the core of the sun, what's going on. Okay? How do we detect them? That was a puzzle, actually. It's a big story. So neutrinos come in three flavors. The neutrino that we're talking about in here is of the type electron, because they're associated with this positron that is produced. And positron is just an anti-electron. So there's neutrinos of the type of neutrons. Here, in the detectors that were in the initial detectors, one of them was Kamiokande in Japan, and another one in Canada and everywhere else. Now they're detecting them. We found only about a third of how much neutrinos are supposed to be. Let's say, for the sake of argument, we're supposed to find 300 neutrinos, just to give them a round number. It's more than that. 300 neutrinos, okay? But because it's very hard to detect them, and we built this extremely high detector in here that is made up of a lot of light bulbs, and each time a neutrino interacts through the weak force with an electron, that's when the light goes on. And if we calculate the probability of that happening, probably out of the 300 electrons, only 3 events will happen in a given amount of time, because the others are going unimpeded. Okay, so if we're supposed to find 3 electrons, let's say in one day, instead of 3 light bulbs basically going on in one day, we only see 1 light bulb. So we have a problem. Is this model wrong, or are we missing something? As I mentioned before, it turns out that the neutrinos don't stay in their flavor that they were formed. They were formed as electron flavor, but they switched to a muon flavor or a tauon flavor. So you start with 300. So what in actuality is happening in this case is only 100 of them are of the type electron that remain. The other 3 they keep on switching, actually, called the neutrino oscillations. So what you're supposed to be then finding, if the model is 300, only you're working with 100. And out of the 100, if the rate is the same thing, 99% go undetected and only 1% is going to be detectable, that is what the experiment was showing, and the model is beautiful. So that's how we know what we know is going on inside the core of the sun. Thank you.